All right, we're going to look at this double integral. I haven't actually specified what the integrand is. I've just left it as a function of x. More specifically, we're going to look at the region of integration, which is defined by the limits of the integral. We note that the y integral depends on x, and therefore we expect a non-rectangular region. So we know that x goes between 0 and 1. So we just look at that, the outer integral, to establish that. Y, however, goes from 0 to x. Now, the line y equals x is very simple to draw. It's a straight line like this. Let me just draw it a bit better. So that's 1 there to get some definitive coordinates on it. What this integral says is that we start at 0 in y equals 0. We integrate up to the line y equals x. So the region of integration is this bit here that's got yellow arrows all the way through it. Let's consider this region of integration, but instead let's swap the order of integration so that we do the x integral first. We have to ask, what are our new limits? If we are to do the x integral first, well, we have x equals y, or that can be expressed as y equals x. We have now fixed limits in y. We start at 0 and we end up at 1 for y. So those limits kind of swap. Right? It looks like they've swapped, but it's not really. It's just that we start here in y and we finish up here in y. However, for any given y, say we pick y star like this, we start at the line y equals x, and we integrate up to the value x equals 1. We could pick a different value there, and so on. So we start at the line x equals y, and we finish at 1. Note, we want a y in the limit, right? We can't integrate with respect to x and keep the x in the limits, right? We need to get rid of x's. So the x limit should always depend on y, not x. So this is the alternative way of describing this integral. This integral here and this integral here are equivalent. They're just in different orders.